So, be careful because what you do say now could be used against you in a court of law.
So if I feel
I'm more worried about myself than you guys, to be honest.
Yeah, sure about saying Kramer's
No, I'm going to filter. No parents can watch these ever. You know what? If in like 3 or 4 years you find out that I got fired, you'll know why. I might be committing proverbial suicide here, but we'll see. Does that even make sense?
I don't know.
All right, sounds good. As long as you sound smart. Okay. So here we go. You should have not a note packet like you've seen in my classes before. Nobody's not had one of my classes and seen these note packets. So you got it right there. Should be no excuses. Let's get after this. This chapter will be challenging, but the really the toughest chapters are chapter 3, 4, maybe even 5. That's not what I want. Yep. Okay. So this whole chapter, we're really in the kinematic stuff, and we're really specifically dealing with in this chapter one-dimensional motion. So we're going one direction or on one plane. Okay. Could you go in the negative and the positive direction? Yes, but we're on one plane. For example, if you were on like an x-axis, you could go in the positive. You could also go in the negative, but we're not going up or down, right? That would be two-dimensional motion. That's next chapter. Okay, we don't ever do three-dimensional motion. That's on a much higher level. Okay? Sprites. So as you guys know, motion's all around us, so it's just really something we can't get away from. So we're going to start studying specifically just one-dimensional motion. Okay, to simplify the concept, we're going to start easy, so we're going to simplify this, and you're going to find out that this physics class, physics is supposed to be like real life stuff, but honestly, we've really dumbed it down to make it easier for us. For example, we pretty much treat everything like it's in a vacuum, and we treat everything like there's no friction. Not everything, but a lot of things. And why do you think we do that?
It's hard.
Yeah, it's hard. Yeah, it's hard. And we don't hardly ever talk about air resistance. Imagine trying to take, the wind into consideration, like what snipers have to do, right? Great. I'm sure it's not like they're doing math in their head. There's probably some program they use, but what? And they're good. Yeah. Sure. Okay. So we're. That's not what you said. And they're gone. What did you say?
And they're gone.
Okay. So we're gonna just stick with one-dimensional motion. So the real great example here, the train going on a straight track, one direction. Could that train go in reverse?
Yes.
Yes. So it's still in the same plane. It's still one-dimensional. All right. This I'm going to camp on this for a little bit. I know that we have probably talked about it in physical science a little bit, but this idea of frame of reference. Okay. To measure motion, you must choose a frame of reference. Notice it says choose. Who's choosing? Yeah, yourself. Okay, you would have to choose on every physics problem how you're going to look at the physics problem, essentially. Okay? And you can look at it however way you want it. Now, I will say this. No frame of reference is wrong, but is there a best frame of reference?
Yes.
Yes. You can use any frame of reference you want, however, there is usually one that is the best for the situation. For example, if I wanted to study the motion from me standing here and walking over here and stopping, there's really probably two okay frame of references. There's one really good one. The best frame of reference would be from the starting point. Because then I would be going in the positive direction and I wouldn't have any negatives involved. Okay? I could choose the frame of reference of over here, and it's coming at me. That one's still easier than some others, but now you're looking at it from a different direction. You could choose the frame of reference from right in the middle, But then you would have a positive direction and a negative direction. Do you see how that becomes a little bit more complicated? So is there a best way to view motion? Yes, there's a best way. And it's not as complicated as you think. It's really pretty self-explanatory when we start doing it, but it's just very important to know that we get to choose what frame of reference we use. Okay, questions on that? Does that make sense? We'll get into some problems and we'll be fine. All right, displacement. I know it's been like 4 years for some of us since we last talked about displacement. What's displacement? Without looking at your notes, I know it's right in front of you probably.
Rock and water to figure out.
That's water displacement. That's something different. Okay, I see what you're saying.
Isn't there moving something from this position? The amount of time.
It's displacement.
The distance it takes you to get from point A to point B, like fully. No, that's like.
So there's 2 words here. You cannot.
You can't use distance.
So you talked about distance. Distance and displacement are similar, but they're very different at the same time.
Is it like the sum total of the?
Okay, let me show you an example. Let's say, I should probably define displacement before I do this, but let's say I got point A here, and I got point C.
No!
Oh, that
Almost made it so. It's Harry.
Point B here. Okay? So let's just say this is the school and this is your house, or vice versa. Okay? So a car leaves point A, travels to point B, and stops. Okay? Is there any difference between the distance and the displacement of the object?
Yes.
Not here.
Not here.
No.
Distance and
Okay? Distance and displacement are the same in this case. Now I'll tell you what displacement is here in a little bit. Now, second situation, I go from here, I turn around, and I go back. Is distance and displacement the same here?
Yes. No.
Yeah, it'll make more sense. It'll make more sense when we define it. Displacement is a change in position. And here's your first equation.
Big green equation.
Oh, is that a job?
Dad?
That was a.
A zing?
Is it all?
Zing.
Zing. Zing. What class was that? Was that your measure?
Oh, yeah.
Yeah.
Classic
What
crazy.
was the context?
Still making sure.
You just write it down.
You probably roasted Cheyenne.
No, I never rolled.
You bet.
All right.
Wait, that's awful.
So, displacement is this is important, a change in position. Okay? Notice, displacement is not always equal to the distance traveled. Distance traveled is total amount of steps something has been taken, or the amount of, I guess it's hard to define. I can't define distance with distance, can I? That doesn't make any sense. It's the total movement. Okay? Displacement is going to be the difference between your starting position and your final position. In the second situation, what's the difference between my starting position and my final position?
Nothing.
Nothing. So its displacement is?
Zero.
0. Making sense now. What's the distance traveled though?
Twice.
It's twice what it was in the first situation. So let me give you an example of a difference between like distance and displacement. Maybe. No, that won't work. I'm not going to say it. Okay? So, here, in the very first situation where I just went from A to B, the change in position or the displacement, let's say it was for 400 feet. Okay? What was the distance traveled? 400 feet. So distance and displacement were the same thing.
Yes.
Okay? In the second situation, our displacement was 0, and our distance traveled was 800. Okay? So it's very, very important. So the main difference between this, do you guys remember these two very important words? vector and scalar.
Yeah.
Wait, wait.
And direction. Oh,
Scalar is just one of them.
Yeah.
Is that right?
So scalar has no direction.
Yeah.
Vector, oh yeah, one of them, that's
Yeah.
Vector is direction and magnitude. So it's both. So if you want to write that
That
down,
makes sense. So scalar is either. No.
Scalar is
scalar
just
is only magnitude. And you can say no direction if you want. And vector is both magnitude and direction. And I don't know if that even, it may come up in your notes later. I'm not sure if it will. What the big thing to get out of this here is distance has no, direction has no impact on distance. It's just total travel. That makes sense? However, displacement, direction is very, very important. Okay? And if you think about everything we've done in math, most of the things you do in math are vector related. Right? You need to know where you are on that number line, right? Okay, when you subtract, it just means you're going in the negative direction at a number line. That's all it means. I think I've said this before, but I remember when I first realized that was like a big earth-shattering, it helped me understand a lot. To realize that when I'm subtracting, I'm just going left on a number line. That's all that means. Okay? So everyone got, I know you guys don't probably all have a note card, but you're going to need to get a note card to do this, and I'm sure you could probably just ask somebody and you can get it pretty quickly. Question?
Can we put the
Oh, great. I think I know what you're saying. Here's what you can and cannot put on your note card. The only thing you can put on your note card is an equation. You can put no words.
Okay. So I was gonna put like one of
No units, no nothing, just equations. So I'm saving you the time of having to memorize the equations, but you need to know how to use them.
Wait, so we can use these on all our tests
All your-
and finals?
All your tests, all your quizzes, everything. Yes.
But we can't know like change of X, or.
Yeah, you like if you have this equation on your note card, you have no idea what change in x is or what xf and what xi is. Can you use it?
No.
No. So you're gonna have to know what they mean.
So
That makes
can I put
sense.
final line?
Yeah.
Does anybody need to know?
Sorry, dude.
Okay. Does that make sense? So maybe if you thought you were gonna get away with putting whatever you want on there, no.
Is there too much?
And you can't put displacement.
No words.
Gotcha.
Absolutely no words, unless in the equation there's a word. But
That's fine.
okay, no words, nothing but the equation. Okay? So you need to be able to know what each of the things in the equation mean and how to use it. But we'll do it so much that you'll be fine. Are you cold, Jesse?
Yeah. It's
You want my
literally
coat?
freezing in here.
Ooh.
No, it's so cold.
Two.
Literally.
So
Literally.
you pull over
Literally.
and then it's just
I got a second coat if someone else wants it.
Can I work it?
You want it?
No, Emma, why are you
My
not?
hands are kind of cold.
Okay, I feel good right now. I don't know why. Okay. Questions on this? You're going to see this changing a lot. And that's the Greek symbol delta. I think we've talked about this in the previous class. I mean, I know the advanced chemistry know this like the back of their hand. But this is the Greek symbol delta, which means changing, which is final minus initial. Okay, you'll see change in time, change in velocity, change in unit. So this is just kind of showing you how displacement. So if you're talking about distance, you're never going to have a negative number with distance, ever. Even if you go in the negative direction, because it's just total steps or total amount traveled. Okay, but you can have negative displacements. And if you look at it, think of it as on a number line. Maybe I should put this up here. I mean, I realize that you guys know like the quadrants of of a coordinate plane, right? But this would be positive, positive. This would be positive, negative. This would be negative, negative, and this would be what? Negative, positive, right? That doesn't probably make any sense, but you guys know how that works with a number line, correct? Okay. The point is, if I were to travel left on the x-axis, if I were talking about displacement, I would need either a negative symbol or I would need a specific direction. Not both. For example, if I went from here to here, and that was, let's say, 8 meters. I can either say negative 8 meters, that would be one way of describing this from a displacement standpoint, or I could say, assuming this direction's west, I could say 8 meters west without a negative. If you put a negative and west, now it's like 2 negatives. Does that make sense? Okay, so there are 2 ways, and a lot of times, listen, this is very important. A lot of times when I'm doing the math, I keep the negatives out. I do the math without negatives, and then my answer, I just add a direction based on the context of the problem. Because if you're doing only multiplication, division type stuff, do the negatives matter in the process along the way? No. Now, if you were doing this displacement where you've got subtraction or addition, then it's important that you put in negatives. Okay? So, but most of the things we're going to do don't have any addition or subtraction in it. It's just a whole bunch of multiplications and divisions. Alright? So just be we'll talk more about that when we get into some problems, but it's very important to realize that math gets a lot easier if you can remove the negatives, right? We'll talk about that. So this is showing, right, if I go from here to here, we got a displacement of 70. Final minus initial. So 80 was the final, 10 was the initial, my displacement was a positive 7. You can see all of those different things. Notice the ones that are pointing left, what do they have in front of them as their answer? All negatives. Okay? But if we were talking distance, would they have negatives? No. Average velocity here. There's your second equation.
So would V average count as a word?
No.
Okay.
So that's part of the equation,
Okay.
so yes, you can put that in there.
I mean, yes.
Kramer, does,
Do I have to put you in the back there?
no, I already.
I
wrote it
would
down.
have it. She's telling about skin.
I was.
A girl who
Does
has
X,
excess skin.
does X always mean displacement?
Yes. Well,
In
Yeah.
physics?
yeah.
I feel like you always do that in our study, but in other stuff.
Well, you know, I mean, if I say a word, does it always mean this? Does it mean the same in my context if it does in like Jewish context?
On video.
I'm serious. I mean, do you think if you read the Bible as if each word means the same thing in every context, you're not reading it correctly. Just look at Revelation. I'd love to talk about Revelation, but I'll stay out of that.
Do it.
Okay, so average velocity here. Total displacement divided by the time. Could the displacement be 0?
Yeah.
So your average velocity would be 0. Does that mean you didn't move? No. So you got to be very careful here. For example, if this is a great example. If that's not a great example. I have to think before I show you things sometimes. You realize that. What? Sensors of video. Yes. No, so technically we haven't gone over what change in time or time interval is. So you can put this in your note card if you want, but this. So yeah, it's it's t final minus t initial. So So anytime you see that change, it's always final minus initial. And that's almost the only the context we'll ever use is going to be a change in time. So we're not going to see any different. Yes?
So like if you're pitching, throw it, the catcher throws it back to you, the velocity is actually 0.
Yeah.
Then
I know, it's hard to think of it that
The
way.
ball isn't really kind
so it's speed, not velocity.
of speed.
Yeah, that's why they don't say the velocity of the
Well,
ball.
Well, people
Yeah, they use it wrong.
They throw it, well, yeah.
The word's irrelevant.
Yeah.
Yeah. But if you said, I'm going to study the travel of the ball just from the pitcher to the catcher, and I left it at that, yeah, you could talk about velocity. But if you wanted to say the whole time from going to the catcher and back, then yes, then we would do it.
Oh my word.
All right, here's some really important stuff here that is so subtle and so small, at least you might think it's not a big deal. We're going to start coming across a lot of different variables. I mean, we've already, in the first day, we've got x, we've got v, we've got t, 3 variables already. So we're going to come across a lot of different variables. And part of being good at doing math problems is, guys, the math isn't the hardest part about physics. The hardest part about physics is identifying what type of problem it is, what are the variables, what equation I use, all this stuff. And because an equation, in a problem, it might not say the velocity is. It might say you're traveling at 24 meters per second. Well, what variable is that? That's actually speed, because I didn't give a direction.
What if you said meters per
But if I said, yeah, if I said he traveled 24 meters per second west, that is what? Velocity. Okay, so you have to be very, very careful. There's a couple of things you need to be able to distinguish. Is there a direction? Okay? And what does the unit tell me it is? Units are important, very, very, very important, because when we get to acceleration, the most common unit for acceleration is a meter per second squared. Velocity, it's a meter per second. So it's not going to specifically say, hey, this is what the variable is. You got to figure it out based on the context of the problem, and a lot of times based on the unit. Look at the units. The units should tell you a lot. So that means you probably need to know what is the most common unit for velocity. What is the most common unit for acceleration? Well, it's telling you. The most common unit for velocity and speed is a meter per second. Does that mean I couldn't do a feet per hour? I could still do feet per hour. It still could be that. But most of the time you're going to see a meter per second. Okay? Very important.
Velocity has to have a distance in it, or
Velocity has
or
to
a
have-
direction.
What was that?
A direction.
Yes.
The problem. So if it says just meters per second, it's speed. Is there a speed equation that we're gonna learn?
Yeah, I think, yeah. We'll learn it. Well, I don't know if we'll ever even use speed. I'm trying to remember.
What did you see without, with like distances and everything?
Yeah, well, speed is just distance divided by time.
Yeah.
So if you want to write that, you can. So it's, the difference is speed is distance divided by time. Velocity is displacement divided by time. Okay, so speed is to velocity as distance is to displacement. Is that too much?
No.
That's true.
I just got
Okay,
so lost.
so here's the thing. So scalar would be distance, and speed are two scalar quantities. Vector quantities, what relates to distance but is vector would be what? No,
Wait,
Displacement.
displacement. It relates to distance, displacement. And what would relate to speed but is the vector version of it?
Velocity.
oh, so I just switched them.
Yeah. Okay. I'm trying to think what's next. Before we do that, well, let's do a problem here. I'm going to just make up a problem quick. Let's say, I don't know if you don't have this one in your notes. A car trip to a friend's house. And you don't have to like write this in, just follow along here. this is going to even make sense as you read it, but. Okay, so I realize that the progression of how this sounds probably doesn't look real well, but you get the question they're trying to ask here, right? So I'm starting at a particular location, my house, and I'm going to my friend's house that is so much away, right? And it takes me this much time to get there. What is the velocity? So here's how we would break this down. We're going to talk later about when we're doing these math problems. I know this one's a simple one, right? But when we're doing these math problems, the very first thing we should do is identify and label what we have. Okay? Now, if we read this up, did it say the blank was this?
No.
It didn't really tell us what this is, but if we read the context of the problem, what is that? Displacement. Why is it displacement and not distance? West. Now be very careful. You could do this one of two ways. I'm going to do it, so change an X. I'm going to put a negative on it because it says what? West. West is the negative direction. So I'll say negative 370. Now I said that you can ignore the negatives in some context, and I'll show you both ways here. Right? And then what is this telling you? So your change in time is what?
5 hours.
And what are we solving for? It would probably be the average velocity is what we've only given you at this point, right? So you would look at these variables, you would look on your note card that has 500 equations, you would probably figure out and look and see which is the equation I should use in this case, in this context. Probably the average velocity one, right?
Yeah.
So then it would be as simple as taking this divided by this. And what do you get?
74 kilometers per hour.
Negative 74 kilometers per hour.
I said per second.
That would be one way of doing it. Or you could also say what?
74 kilometers per hour.
So did I really need that negative?
No.
No, I could have kept the negative out, done the problem, look at the context of what was going on, and plot the direction on it, been good. So do you see how you, in a lot of situations, you don't even need to put the negatives? Be careful, if it has addition or subtraction in the equation you're using, you're going to need the negatives, because then it becomes, then you're going to have to use it.
What if the pump hadn't said right?
Then you would have to treat it as a speed probably. But it would still be 74. It'd be 74 kilometers per hour, but you wouldn't have a direction.
Because here, in this case, they were.
Okay, I don't want to spend too much time. Oh, there it is, average speed. So there's the equation that you were wondering about, Shane. So instead of putting this in your notes, this would be S equals D over change in T. Does that make sense? And I'll be honest, it's kind of frustrating. Your book makes quite a few mistakes. Sometimes it will want you to solve for speed when it really gives you stuff for velocity, or it'll want you to solve for velocity when it really gives you only speed stuff. And so you're going to have to just bear with the stupid thing. All right, we've kind of already talked about the difference, kind of how distance and displacement are related. It's the same thing for speed and velocity. Speed has no direction, only magnitude, and velocity has both. All right, this is good. I know that students struggle with interpreting graphs.
You
All right.
lied. On the ACT, there's like 2 graphs.
Really?
There's
No.
all, no, it was mainly reading. It was like, hey, let me give you
They're like
a book about
experiments.
experiments and then look at the graph.
All right, we only have 5 more minutes. I want to make sure we get done here. Okay, so this would be a position versus time graph. Okay? We can determine the average velocity by drawing a straight line between any 2 points. Now here's very, very important. If the velocity is constant, what does constant mean? It's not accelerating. The velocity isn't changing. It's like you put it on the cruise control. Does that make sense? You're going at a constant velocity if you put on the cruise control. If it's a constant velocity, your position versus time graph. Is this a velocity versus time graph?
No.
Position versus time graph. It will be a straight line. That means whatever my rise and run is the same because I'm traveling at the same speed. Now, if my velocity wasn't constant, your position versus time graph might look like this or like this. Okay? Because at some points you have steeper slopes, and other points you have not so steep slopes. You've got some negative slope in there. What's the connection between velocity and position then?
Linear.
Kind of. I mean, this is probably some big words that some of you don't know yet, but velocity is the derivative of position. And acceleration is the second derivative of position. Okay, well, we're not going to do calculus in here. Don't worry about that. You're looking at me like, what? Okay, the point here is you can figure out what the velocity is by looking at this. Find the slope. If you know the slope, that is your velocity. So listen very carefully. The slope of position versus time graph is your velocity. So here, do I have a positive velocity or a negative velocity? Positive. Now we don't know the actual magnitude at this point because we don't have numbers here. Okay? What about this one? What can you tell me about this one? It's not even moving. Well, you can tell on the position it's not moving, right?
Well, that was the baseball.
Velocity must not be moving.
The baseball direction's going up.
Okay? So, the point I'm trying to get here is, if you're looking at position versus time graph, you can figure out velocity by looking at the slope. Okay? Now let me show you what this next one would look like here. Instantaneous velocity. We will not do anything with instantaneous velocity because it involves using calculus and derivatives. But I do want to give you some, at least show you what it is here. So this is still a position versus time graph, right? Is velocity constant?
No.
Why is it not constant? Who can tell me why it's not constant here?
Because it was accelerating.
Yes, but how do you know that?
It's a curve.
It's a curve.
Oh.
If it was a straight line, you'd be going at constant velocity. You can see there's a change in its position. Not just a straight change, it's a curve change. Okay? This, if I took and went like this, that would be constant velocity. Every so many seconds I'm traveling the same distance. But is that the case here? What's happening here to its velocity?
It's accelerating.
It's speeding up. You can tell looking at the position versus time graph. So it's not, the velocity here is not the same as it is here. But in this here, would the velocity here and here be the same?
Yes.
Yes, the slope's the same. So, now we're not going to do this, but I want to give you some information here. Instantaneous velocity is what is the velocity at that one time? For example, if I find average velocity, and I say that it traveled 74 kilometers per hour, does that mean the whole time it was traveling 74 kilometers per hour? No, it could have been traveling faster at one point, slower at another point, right?
Yeah.
Okay? So what we did before was an average. Okay? Instantaneous is what is it at that specific point in time. And here's how you would do it. I'm not going to make you compute it, but you need to know how. So listen carefully. If you want to figure out what the instantaneous velocity is you would take a line and run a tangent to your point. Does anybody know what running a line tangent to means? It's like taking a straight line and getting it, the only place it touches is where you're trying to figure out what the velocity is. Do you see this tangent line? Ooh, I like that. If you took the slope of this tangent line, you could figure out exactly what the velocity is at that point. And I could do it at every other point on this graph. Okay, now we're not going to do it, but I just want you to know, if I want to know instantaneous velocity of something that's a curved position versus time graph, I would take a tangent line and figure out the slope of it. Okay, I think we're done. We never did get to the last homework, or last example problem. But yeah, it's 825 meters to the east. If you want to write that in and try to make it work out when you're working through it.
Yeah,
825 meters to the east. Or you could say positive 825.
Oh, yeah, you should.
It's really similar to the one I just did.
Yeah, it's just they give you the last.
Yeah. It's not a hard problem. We're not going to need a hard problem.
I like that. That's what I was looking for.
Most of what we did today is getting familiar with vocab.
why is this so cold?
Yep.